Thank you, Debbie. Good morning, everyone. My name is Kati McKenna, and I am the SME Engagement Lead for the National Manufacturing Institute Scotland. Welcome. Welcome to our NMIS webinar, High Strength Hybrid Hydroform, Exploring Hydroforming Potential Applied to Tailored Blanks. June, can I have, please, the agenda slide for today? Thank you. So briefly, the agenda today is there will be an introduction, short introduction to NMIS by myself, followed by the main part of today, the two presentations by our three speakers. And in the end, we will have ample time for question and answer afterwards. So can I have the next slide, please? So I would like to introduce our speakers today. Dr. June Liu is a manufacturing engineer of the Advanced Forming Research Center, AFRC part of the NMIS. His background is metallic materials and manufacturing engineering, mainly on sheet metal forming technologies. He received his PhD in 2013 with a focus on development of a novel superplastic forming process using aluminium and titanium alloys at lower temperature and faster forming conditions. Before joining FRC, he was at the Imperial College as a postdoctoral researcher working on hot stamping technologies for lightweight applications. June has expertise in materials characterization, microstructure, forming processes, FE simulation. He is now leading the research projects at the FRC on the development of lightweight manufacturing technologies for automotive and aerospace applications. Our next speaker, Ahmed El Said, is a manufacturing engineer and FE modeler of the FRC. He received his MSc in mechanical engineering, mainly focused in sheet metal forming technologies. Ahmed's main experience is in FE simulations, material modeling and characterization, and cold sheet metal forming processes. And our guest speaker today, Mark Brazier, is the CEO of PAB Coventry Limited. Mark has been involved with the business since its creation in 1986. Mark, while still at school in Rugby, would walk to the factory after school and help his father out in the office or put some overalls on and help on the shop floor. Mark completed his apprenticeship and worked his way through most of the areas within PAB and became the managing director in 2004. He is responsible for the strategic growth and direction of business. Thank you. Can I have the next slide, please? So just a couple of items of housekeeping. This webinar is being recorded and will be made available on YouTube channel. Your microphone and webcams will be turned off during the session to avoid background noise. You can type your questions. We very much invite questions for our Q&A session throughout the session via the chat tool. Please use the chat tool for your questions. Time will be allocated at the end for the speakers to answer the questions, and because I hope it's going to be ample time. And please take some time to complete our survey that we will be sent after the webinar. Next slide, please. National Manufacturing Institute Scotland is a group of industry-led manufacturing research and development facilities where research, industry, and public sector work together to transform skills, productivity, and innovation to attract investment and make Scotland a global leader in advanced manufacturing. Next slide, please. Here, a couple of lines on our strategic vision. So our center aims to increase productivity by reducing barriers to innovation. We aim to stimulate investment and increase manufacturing competitiveness. We support catalysis of job creation and strengthening of supply chain links. We also do a lot of work to inspire and attract talent and equip current and future workforces with the right kind of skills, particularly in the areas where shortages of skills are experienced, such as digital manufacturing of the future. We work as an organization, we work with manufacturing businesses of all sizes in multitude of sectors, providing benefits across the whole of Scotland. And as today's example will tell you, we also work across the UK with the industry stakeholders across the UK, and in particular SMEs. Thank you, June. So NMIS is operated by the University of Strathclyde, and we're also supported by our partners and funders in the One Scotland team, which include the Scottish Government, Scottish Enterprise, Highlands and Islands Enterprise, and South of Scotland Enterprise. We're also working locally very much with the Renfrewshire Council, where we are physically located. Scottish Funding Council are also our supporters, and Skills Development Scotland, of course, very important as per our skills agenda. And of course, last but not least, our center is also a member of the High Value Manufacturing Catapult of the UK, a constellation of 7 catapult centers across the whole of the UK. Next slide, please. So just a brief overview of what the NMIS group consists of. We are a group of several specialist technology centers, and we're also very much supported by a very active network of partners in the manufacturing community, and that includes not only the HVMC community, but also academic community across Scotland and across the UK as well. So the Advanced Forming Research Centre, in particular, focus today focuses on technologies such as incremental near net shape forming and forging, of course. Residual stress measurement is another element of what we do. And also, basically, we do all kinds of work in engineering in metallics pertaining to materials and components. So the focus is mostly on metallics, but also on other solid materials. That brings me on to our lightweight manufacturing center. They focus more on composite and composite component type of research, but also other broader issues pertaining to lightweighting in other materials as well. So we also have an important part of our institute is the Digital Factory, and Digital Factory covers digital manufacturing and a number of sub areas of Industry 4. Measuring and sensing, connectivity, visualization, automation, data analytics. We also, within the Digital Factory, cover design, product design, new product design, product realization, additive manufacturing, all manner of advanced and more traditional machining as well. And within the Manufacturing the Skills Academy, we focus, as the title says, on delivery of improvement in terms of skills, and that includes a variety of CPD courses, academic placements, knowledge transfer partnership, PhDs, NGDs, and graduate placements. So thank you for listening to my overview of NMIS, and I will now pass the microphone on to June to start his presentations. June, the stage is yours. Thank you.
Thank you, Katia, for your introduction. Okay, here comes to our research work. This is the introduction of my research work. Our research work funded by the Niche Vehicle Network and the AFRC internal funding. And the 4 AFRC forming team had collaborated with PAB Coventry to identify a new way to manufacture lightweight, large, and complex vehicle components. Automotive and aerospace sectors are quite distinct in terms of production volume, quantity requirements, manufacturing cost, and product development lead time. So this webinar is to showcase a high-pressure forming technology originally developed for the aerospace sector and explore its potential adaptation to the automotive sector. A good understanding of the manufacturing challenge of the beneficial sector is required in order to propose successful cross-industry transfer. So, low and medium volume automotive sector and in service part replacement market have been targeted with the technology demonstrated in this case study. Here comes the background of our research. As the world pushes towards net zero emission targets, there is increasing demand across the automotive sector to reduce vehicle weight and therefore CO2 impact. This drive spans the entire industry from mass-produced models to heritage cars in the niche vehicle sector. So, hydroforming process is understood to have significant potential to enable forming of a great range of sheet metal materials for industrial application. In this case, lightweighting aspect is one of the objectives targeted by the process. Hydroforming can provide simplification in terms of the process steps or the tooling. Simplified manufacturing approach is an essential requirement to any industry, particularly in forming aspect. So reductions in the numbers of process steps or in the tooling result in cost saving and less maintenance requirement. As shown in the figure, in the conventional forming process, different parts are formed separately and subsequently joined together, where in the proposed approach, we use tailored blanks as the raw material, where blanks are joined together prior to the forming process. Tailored blanks offer an opportunity for weight reduction, while maintaining the structural integrity of the part. Definition of the process variables and the subsequent optimization are investigated to form those complex parts. However, there are still some challenges to be addressed in our research work. The main challenge was to understand if the hydroforming technology could be applied to form an apinal part consisting of different thickness, which is tailored blanks in our case. This was addressed by validation on existing cross-forming process using homogeneous blank. Potential problems like uneven deformation or wrinkling of the material were to be overcome. In addition, further challenge lie in the design of tailored blanks. As you can see on the right side of figure, every simulation was performed to optimize the blanks with dissimilar thickness or property of tailored blanks. And how did the NMIS and AFRC help? The team was able to validate the feasibility of the hydroforming technology applied to the tailored blanks for an apinal component. The validation was done at the simulation level, and it is unexpected that experimental trials will show very similar results. As a consequence of this analysis, industry could form a lighter component through a simple and less costly tooling, while maintaining the strength and the rigidity of the original part design. The AFRC team had developed an FE model to explore the feasibility of this approach, and the analysis compared different forming approaches, including homogeneous thickness and the similar thickness of tailored blank. And this research had provided a high degree of confidence to the AFRC stakeholder, especially for the PAB Coventry, that the proposed technology is technical and commercially feasible. The result provided a component with saving of 24 with a maximum 28 thinning in the material thickness within existing design parameters. The result also opened the door for further manufacture of complex shaped components with greater material or design flexibility, presenting opportunities in other industries such as defense, aerospace, and rail. Here comes some results from our research. In our research, we take the apinal part as an example to explore. Currently, the apinal part is manufactured by stamping process. As you can see from the figure, this part is manufactured by stamping process using cross-forming tool. In the case, 60 aluminum alloy 616 where the initial thickness of 2.5 mm was used. Forming trials and simulation have proved that the minimum thickness close to 2 mm was achieved after forming. The corresponding thickness reduction is 19%. And the selected material had been tested under uniaxial tension and various stretching conditions for the aluminum 6016. As shown in the figures, no significant variation in stress or strain was found along different rolling directions, indicating the material is fairly isotropic. The forming limit curve was also obtained, which will be used to determine the material formability at complex forming conditions. In the next few slides, I will invite my colleague Ahmed to introduce modeling and tooling design part.
Thank you,
Pass my microphone. Yeah.
Thank you, John. So after the material testing and material characterization, now we can start with the material modeling. Three main sections for the material modeling must be identified. First is the hardening curve. Second is the yield criteria, and of course, a failure criteria. For the yield criteria, we decided to go with Bartlett 2000 after comparison with different yield criteria. While for the failure criteria, we of course have the formal element diagram for the initial thickness of 2.5. We can next, please. Now we can jump to the tool design. So originally we investigated two setups. First is the concave for this type of setup. Of course, we have two general setup, which is a bunch and cavity tool, but here we decided to name it as a concave and convex because of the type of the shape. For the concave here, we decided just to do a simulation to judge the flow of the material. So by applying a fluid pressure, we can see some wrinkling that can appear in the part, which means that the material is not flowing very well. And that is because the different of the height of the edges of the two parts. Next slide, please. We decided to go for the different setup, which is convex. So here we judge the tool flow, the flow of the material. So it is very important here to consider two main things: is the ability to form the small corners or the deep corners that with small radii in the part, and also and this should be done by achieving full contact with the tool surface. But also we must consider here avoiding tears of these small features. Next slide, please. So this is the final setup that we decided to go with. The maximum power is between 800 and 850. We will apply a fluid cell for the pressure. It is very important here to consider the load, the loading of the tool itself or the pressure. So if we look to the image in the right, and if we have a straight line from the initial load to the maximum load, so above this line we have stretching or high stretching, which is considered in the orange curve. But you need to take care of the tears that might happen as well. In the yellow curve, sorry, in the blue curve, we have the low stretching, which is low loading curve, but you might have some level of wrinkling. So next slide, please. So as I said, you need to have a balance between the two loading curves. Here also is an investigation for the effect of the blank shape and also the loading curve. So and its effect on the failure of the part especially in the small corners. So we can see in the first image on the top right, we have small failure in the some failure in the small corner there. But when we still just change the tipping angle or change as well the blank shape, this can change the amount of failure that you have. And this is mainly because the amount of blank holding that you are controlling during the hydroforming process. So you should consider mainly the blank shape and as well the load curve that you have to control the material flow and have a balance between flowing of the material and stretching as well. Next slide, please. So I will let my colleague Junlu continue the results for you. Thank you.
Thank you, Ahmed. Okay, after a series of blank design, a final optimized blank had been obtained. In order to explore the forming potential applied to tailored blanks, two analyses were performed, and including the homogeneous thickness blank on the left side figure with the original thickness of 2.5 mm, and the tailored blanks with dissimilar thickness with the thickness distribution of 1.5 to 2.5 and 1.5. Here you will see on the left the FE simulation result for the homogeneous thickness blank. The minimum blank thickness after forming is 2.14 mm, corresponding a thickness reduction of 14%. You may still remember that the crash formed part in production shows a maximum thickness reduction of 17. So the hydroforming indicating a high potential for a slightly more uniform thickness distribution. On the right side, you can also see that the tailored blanks with dissimilar thickness. Here, in this case, the original thickness distribution is 1.5 mm on the two sides of the part and 2.5 mm in the middle of the part. The minimum thickness blank thickness is found on the center part of the blank with a thickness reduction of 20%. And formability analysis shows similar post-form quantity by comparing the homogeneous blank and the tailored blank. From the pictures, we can see that three regions, including wrinkling, insufficient stretching, and safe regions. Wrinkling is the result of complex loading with compression and tension stress due to the nature of local features. Insufficient stretching usually happens where there is a limit straining. Safe region definitely indicated that the formation is within the forming limit. It can be seen that the strains for all the elements are far below the forming limit curve, indicating the feasibility of the hydroforming process. The feasibility of the hydroforming process in the forming of blanks of which homogeneous thickness and dissimilar thickness. FE simulation also provided us with the opportunity to investigate the key process parameters, including the press cycle, friction effect, blank design, toning design, etc. Future process optimization could consider these factors and further validate against the experimental trials. Okay, here comes the summary of our research work. Feasibility of the hydroforming technology to form a tailored blank, tailored thickness A-pillar was proved by simulation. When applied to tailored blanks, the hydroforming allowed for a simplification of the process, as low upper tuning is required. Also, avoiding the blank holder problem. This results in cheaper solution, which also would require less maintenance. In terms of lightweighting, the early tailored solution resulting in a potential weight saving of 24%. By using the tailored blanks, the weight is calculated at 0.71 kg against the original design of 0.93 kg. In addition to the weight saving capabilities, Taylor blanks also allow various different parts being formed simultaneously and consolidating multiple operations such as joining and forming. FE analysis had proven to be critical in the analysis of new forming strategies enabled via novel technology. Overall, the case study had demonstrated the potential of cross-industry innovation for niche, low, and medium volume sheet components. Finally, our research work is supported by the fundings from AFRC and Niche Vehicle Network. Thanks are also given to PAB Coventry for their support in the design and testing. So that's all for my slides. And in the next, I will pass microphone to Mark Brader, who will introduce his company, PAB Coventry.
Thank you very much, John. Just going to get my shared. Hopefully everybody can see that. My name's Mark Brazier. I'm the CEO of PAB Coventry. We are tier 1 sheet metal manufacturers into mainly the niche vehicle sector, automotive. We also supply into aerospace, defence and sort of general industries. So I'm going to give you a little bit of history about PAB and a bit of a corporate video, so hopefully the bandwidth will hold up, and then I'll give you my ideas of where I see the hybrid hydroforming helping within the niche vehicle sector.
No voice. Mark, there's no voice.
There's no sound, Mark. I don't know if you can turn it on.
Sorry?
No
We
sound.
can't hear the sound of the video.
Oh, okay. Just try that again. It was me. I didn't click that button. I do apologise.
No problem at all.
Let's start again. Can you hear that?
That's perfect. Thank you.
Have you ever seen sheet metal turned into speed? Or sheet metal turned into art? What about sheet metal turned into a solution? From the automotive and rail industries to defense and vehicles of the future, we've forged partnerships with some of the most technologically advanced organizations on the planet, working with them to solve complex problems by developing truly remarkable solutions. We design, we cut, stamp, shape, weld, and assemble, all to the tightest possible tolerances. We provide bespoke sheet metal solutions for clients who demand the best at nothing less. And we've been doing this for more than 3 decades. In that time, we've delivered every solution our clients have asked for, and a few they didn't even realize they needed. So if you want to see sheet metal turned into the solution you're looking for, you've come to the right place. PAB Coventry.
So a little bit of history about PAB. As Katia said, it was the business was set up in 1986, and it started supporting panel modification to Leyland DAF fans over in Birmingham. Over the 35 years it's been going, we've now grown into 60 plus personnel, and we're constantly trying to increase turnover year on year. Last couple of years have been slightly difficult with the pandemic that's been going on. What we try and do here is mix modern technology and traditional skills to offer very bespoke products to the niche vehicle market. So just a little bit about what we do here at PAB. So we do a lot of R&D, and for a smallish company, an SME like ourselves, it is hard. We work with Innovate UK, Horizon 2020 in the EU. We've teamed up with a number of universities, so Imperial College London, Nottingham University, Cobb University, and of course the work we've done with AFRC and Strathclyde. Just a little bit also regarding, we manufacture standard tooling here at PAB. We can simulate standard cold forming and tool manufacture. We have a series of 5-axis lasers, 2-axis lasers to support component manufacture. We make standard basic components. We do a lot of visual components, so Class A sort of meshes, rear exhausts, mainly for automotive. Sub-assemblies, we do body and white assemblies as well, and recently, due to the demand of the quick turnaround, rapid prototyping requirements, we've added 3D printing. So these are some of the clients who we are currently dealing with or have dealt with in the past. You can see they're not the major OEMs, but they're niche vehicle manufacturers, and these are the people we've been dealing with for 35 years. So we know what the end user wants. So a little bit of a conversation really about how high strength hybrid hydroforming can overcome some of the issues of a vehicle manufacturer these days. And I think this process, one of the biggest savings that the manufacturer will take is the reduction in cost of tooling. So no longer does that tooling need to be steel based. It can be a composite. Believe it or not, it can even be wood, as long as it can take a high compressive force. So you have quite a lot of cost reductions there. Obviously, with the cost of steel these days, that's a big saving for a lot of people. You only need a punch. No longer do you need a die or a drawing. So you're making 1/3 of a tool basically. Composite tooling is a lot quicker to machine than steel, and it's a lot easier to make changes and modifications. So I think from that point of view, the OEM will like this sort of tooling package. We can also reduce costs. It's very close to a net shape blank. Sheet utilization is a lot better. We can consolidate parts, and we can put multi-thicknesses like Jun has presented earlier, and multi-metals, so they don't have to be the same metals. They can be formed, not joined probably, but at the same time across the same tool. And also multi-part tooling. So within the process, as long as we can fit the tool on the tool bed, we could have 7 or 8 different tools, all at different heights, all pressing different materials, different thicknesses, and they will all press in a one hit. One of the big things that we're being asked to look at is the sort of cradle to grave cost of a part. So this is going through pre-production, this is going through prototype, production, and aftermarket. Now, because of the tooling so easy to make, we can use a prototype tool, and with a small amount of modification, take that into pre-production, again take that through to production, and then it's a lot easier to store for aftermarket as well. So again, that cradle to grave sort of cost does start reducing, even though sometimes you might pay a little bit higher piece cost. There will be a saving overall. The way that the hydroforming works, you can press extremely complex parts. So you could have complex forming on the top face. You can have complex form on the sides of the pressing, and also you can create undercut, as long as obviously you've got a split tool and you can get it out afterwards. And that's not using cam tools, that's a one-hit process. Also, if you're also pressing aluminium, you can add trimming operations within the tool. So again, it saves for after processing. From a part cost reduction, this process links quite well with ultra high strength steel and aluminium. The pressures that we use in the hydroforming is immense. Basically, it's like taking the new aircraft carrier that the UK has just produced and putting it on an A4 bit of paper, and that's the sort of pressures that they're using here. And I think it allows the niche vehicle manufacturer to use ultra high strength materials at a much lower cost. We're also continuing to work on the project, and there will be further advantages to the niche and low volume market on the hydroforming. So stay tuned and we'll have more information. I'd like to thank you for watching, and I'm going to hand back to Katia now.
Hello again. Thank you very much, Mark and June and Amit, for the presentations. And now we can start the Q&A session. I'm not seeing any questions in the chat just yet. So I might just start by asking some questions myself. So I would like to address my first question to June. June, you proposed tailored blanks to be used in the forming process. Do you have any idea how to prepare the tailored blanks for maximizing the advantages of the technologies, while on the other hand minimizing the factors of additional cost of process operations?
Thank you, Katia. Yes, actually there are many methods to prepare tailored blanks for different sectors, such as automotive or aerospace sector. Some available methods include tailor welded blanks, which is widely accepted by the automotive sector. The tailor welded blank can be processed by laser or fixed stir welding, and in addition, patchwork blanks is a traditional tailored blanks as well. In this case, the reinforcement part was patched to the parent part to enhance the structure or integrity of the blank. And in the recent years, tailor rolled blanks had attracted a lot of attention for the automotive sector. All these three kind of tailor blanks had been widely accepted by the industry. They are also commercially available on the market. Yeah, I have to accept that the use of tailor blanks might incur additional cost slightly compared to the homogeneous blanks, because you have to additional operation to join the blank. However, this cost can be compensated by the saving of tooling cost and the reduced number of post-form operations, such as post-form joining. So in all, the most important factor influencing the application of the technology may be the development of the process variables. So especially for the tailored blanks, you have uneven deformation or wrinkling. So in this case, we have to develop advanced FE skills to predict the press cycle, understand the friction effect, and so that we can design a proper tool and blank shapes.
Mm-hmm.
Yeah, that's all.
Thank you, June. Thank you very much. Thank you for your detailed answer. That's great. We have a question from Dave. I can see Sarah's question has been answered by Laura already. It's a request for an article on the topic, which is exciting. Great. And the question from Dave Halley is given it's not specified to whom, so I assume it's to all our speakers. Given the very high pressures involved, is the capital cost of the equipment high? Also, the pressure cycling will affect stress strain, and how is this controlled?
Maybe I could answer that one, Katia. Yes, it is a high cost compared to sort of conventional presses, let's say. I would say they were probably 3 times the cost. Compared pressure against pressure, it's probably not 3, it's probably cheaper than what you'd normally get, sort of huge tonnage pressures, but from a bed size, yeah, it's probably about 3 times as much. With regards to the second part of the question, what we've found in our tests, and John can jump in there if I'm actually talking rubbish here, but what we're finding is because it's not like a standard cold form draw, and it's wrapping the part around the punch, the strain is more uniform around the component. John, would you like to add any more to that?
Yeah. I can add some also here in this point. So related to the pressure cycle, so mainly the way to control, of course, the strain and the stresses is a combination between the amount of the blanking area that you have. So you can induce the some flow of the material and allow the material to flow, or you can increase the blank size and hold the material, and if you would like to, for more stretching, I mean. So this is how mainly you control it. This is one factor, which is the blank size, and the other factor, of course, is the cycle itself, the load profile, whether you will go for high pressure first and then you go for low pressure, or low pressure then you increase the pressure to the maximum. The amount of holding at the maximum pressure as well help to control in the end the stress, the strain distribution. I hope this answers the question.
Thank you. So no more further questions just yet in the chat. Please keep asking. I might just ask Mark, are there any other potential applications you have explored? You've shown the A-pillar part, but are there any other components?
Yes, I mean the A-pillar was chosen because it's a complex part. It has some very tight radii and some sidewalls that are quite virtually negative, if that makes sense. So virtually an undercut. So we chose that. We thought it was ideal for 6,000 and trials in 7,000 material, but we're looking at all sorts, from standard moving from cold form pressing due to size into sort of the hybrid hydroforming. So yeah, most B pillars we're looking at, patch blanks. I think the good thing with this is you can be a lot more varied where your patch blank needs to be, because you're not drawing between match tooling. It becomes a lot easier. So I think there's loads of opportunity moving forward to develop the process.
That's great, Mark. Thank you very much. One more question I can see in the chat from Matt Kopitz, or Kopik. I'm sorry, Matt, if I'm mispronouncing your name. Matt is asking a question to June. Is it possible to extend the hydroforming to high strength materials like HSS or titanium alloys? I get the first one is high strength steel, yes, or titanium alloys. That's Matt's question to June, please.
Okay, thanks for the question. Yes, I think it's possible, but the material, we have to consider the material formability and ductility at cold forming conditions, especially at room temperature. I cannot give you an exact case on titanium or high strength steel, but for high strength aluminum, we're currently developing a solution for high strength aluminum alloys, such as aluminum 77.5. For this material, the strength is competitive to high strength steel with yield strength over 400 megapascal. So I think this is possible, but still depends on case by case.
I would like to add here another thing as well, which is the capability for the press or the hydroforming press. So it should be as well able to form the titanium alloys, for example, based on the strength of the material. So this is one factor you need to consider as well.
If I wouldn't mind just chipping in there as well, Mark, there has been a lot of development work done on titanium alloys. I can't say too much because NDAs and that sort of thing, but looking at sort of warm forming of aluminium, of titanium, has already been a significant amount of work done on that.
Thank you. Thank you. So I will ask the next question. This is a question to Ahmed. It's about the forming limit curve. You tested the material with a thickness of 2.5 millimeters, but how do you justify it is suitable for the tailored blanks, especially for the thickness of 1.5 millimeters in the simulation?
Okay, thank you. So Katia, so yeah, it is actually true that we only tested the material for the 2.5 millimeter, but the difference actually between 2.5 and 1.5 is not significant. So we used there is like estimation models which is implemented in the FE simulation that can just predict or estimate the formal limit diagram of the different material of different thicknesses when you have a reference thickness that you can give it as an input. So yeah, it can be done when you have a reference FLED. Thank you. I hope this answered the question.
Great. Thank you. Thank you very much. I might just pass another question to June. Does the tool need any compensation for the tailored part?
Yeah, thank you, Katia. The answer is no. The blank is formed by the hydraulic pressure, so which is, in this case, it is very flexible with thickness or strength variation. And if during forming of thinner blanks, the main concern will be to consider the material flow behavior due to the variations in the strength or in the thickness. So in the case, we have to consider the material flow behavior during the tooling design or the process design.
Great, June. Thank you very much. Anyone would like to expand more? I might just ask Mark another question. First of all, I would like to thank you very much for explaining so eloquently, about the commercial benefits, to you as a company, as an SME, of introduction of this new technology. Can you share with us a little bit more about your views on your experience of working with a research organization? What are advantages, disadvantages, or challenges maybe for an SME working with NMIS and the catapult centers?
I mean, in the past, we've worked with, like I say, a lot of the universities, and sometimes it can be difficult working with sort of academia. We're here to produce parts and sell components, and sometimes there's always a clash there. But what we found that we do well here at PAB is we take the ideas from the research labs and see if then it is feasible within an industrial area. And I think we do that well. The fact that we got to a point here where we'd recognised a hole in the market that we could plug with this new technology, and we needed help on a raft of testing that PAB, and I'll hold my hands up, know nothing about, and I don't really want to get involved with it. I want somebody to tell me what's the best temperature, what's the best speed, what's the best time to do things in. And this is where Jun and his team has helped us out, and we probably wouldn't have got anywhere near this far without them. So I just want to say a big thank you to them.
Oh, great. Thank you very much. And maybe I would just draw out a little bit more. What do you see, how do you see innovation kind of helping to deal with the current challenges, in the economies, challenges with the supply, geopolitical challenges, and so on? Do you see a role for innovation activity in that?
Well, as everybody's price of everything's going up, so there will be a big drive to try and cap those costs. Whether you can actually stop them at all is a different conversation, I think. So if there's an innovative new way that can, and I'm just going to take the tooling as an example. We've done a cost comparison on the A pillar that we've done. And we believe that the cradle to grave tooling cost is sort of about 15% of what it would normally be of cold forming. So all of a sudden there's a big cost saving there for the OEM, that's the car manufacturer. Giving the OEM the options to use ultra high strength aluminium. Again, it's a cost-effective way of doing it. We can do it via a W temper, and they don't need the sort of investment that the big boys do to add these to these sort of cars. So I think, like I say, it's a win-win for everybody, I think, on this one.
That's great. Thank you very much. I'm just going to check in the chat. And I'm not seeing any more questions in the chat. So I would like to close our question and answer session now. I would like to thank our speakers again. Thank you very much, Mark, Jun, and Ahmed, for your excellent presentation and the discussion, and I hope it has been helpful to our audience. Thank you all very much. The webinar is at an end. Thank you. Bye.